So hi everyone and welcome to the Applied Algebraic Topology online seminar. The speaker today is Davorin Lešnik and he will tell us about sampling smooth manifolds using ellipsoids.
Okay, thanks for the introduction and the invitation to the seminar. So this is a topic that we did together with Sarah, who just introduced me. So you can actually ask questions for both of us. Now, the topic is actually a rather familiar one. You have an object in a Euclidean space. You know some basic information about it, such as dimension, and you have some sort of access to it, basically some form of sampling, and then you want to determine the nature of this object. There are a lot of variants of this theme, and an example are manifolds, in particular smooth manifolds. A seminal paper on this topic is by Niyogi, Smale and Weinberger. Here's the theorem in a slightly different notation than they used in the paper, but the point is you have a compact manifold without boundary, C infinity, embedded in a Euclidean space. You know some basic information about this manifold, specifically its reach, which is denoted here by tau. That is the distance to the medial axis, which is a basic form of a global feature size. Basically how close different pieces of manifolds come together, because the closer they get together, the denser your sample has to be intuitively, so that we actually determine what the manifold is. And then if you satisfy these criteria here, specifically you take your sample, you expand the sample points to balls of size p, and so long as p is on this interval where kappa is the Hausdorff distance between the manifold and the sample, intuitively this just means that you have a guarantee your sample is good enough that for every point on the manifold has a point in the sample which is at most kappa away. So if you satisfy all of these conditions, then the union of these balls around sample points will be homotopy equivalent to your manifold. The deformation retracts to the manifold via the most standard method. You deformation retract each point in this union to the closest point on the manifold along the direction which is normal to the manifold. And in so doing, you can determine the homotopy type of this unknown manifold from the sample. In practice, in practical calculation, you typically don't actually calculate the homotopy type of the union of balls itself, but rather you build a nerve complex on the sample and then take the homotopy of this complex. And in practice, you are usually interested in homology. There are standard algorithms how to then calculate the homology from this complex. Now, as mentioned, there are a lot of different variants on this topic. For example, you can do this for spaces other than manifolds. A popular example are compact subsets of Euclidean space, or you don't put the conditions based on global feature size, such as the Richardo manifold, but variants of local feature sizes, and so on. But the more general case you take, the greater the density of the sample you require. Here is just a selection of various papers that you can find in the literature on this topic. So this is what we want to discuss here. The topic of this talk is how to improve the density of the required density of the sample. If you try to do something similar as Niyogi, Smale and Weinberger did. A natural measure of the required density is this ratio here between the Hausdorff distance of between the sample and the manifold compared to the reach. Basically, you take the reach of the manifold as your unit size, so to speak, because basically you could imagine your manifold in the Euclidean space and then just scale the whole thing, both the manifold in this space and the size of these balls around sample points, and nothing really changes. It's the same up to the scalar factor. So just take the reach, and of course if you scale everything by a factor, then the reach will scale by the same factor. So just take the reach as your unit measurement, and then if you recall this here, the condition, if you just divide this condition by the reach, by tau here, and by this 2, you get condition that kappa divided by tau has to be less than this number divided by 2, and such a p will exist. So an increase of the sample points to both will exist in such a way that you recover the homotopy type of the manifold precisely when kappa divided by tau will be less than this number here divided by 2. So if you take the supremum of possible ratios between kappa and tau, this gives you a notion of how big of a density of the sample you have to take so that you can still recover the homotopy type of the manifold. And the discussion in this seminar is something that we together with Sarah did to improve this ratio. So the greater the density, the smaller this ratio will be. And since we want to get a small density, we want to increase this ratio by as much as possible. So how to do this? The idea is that instead of expanding sample points to balls, we expand them to ellipsoids. The reason for this is, and here it will be helpful if I draw something. So if you have your manifold, and then you want to have a selection of balls, and I hope people listening to this will find it in their hearts to forgive my drawing skills. So if you have your union of balls, the sample points are the centers of these balls, and they are dense enough so that this union deformation retracts to the manifold. It should be intuitively clear that you will require smaller sample density. If instead of balls you take some figures that are elongated in the direction of the manifold, in the tangent direction, so like this. Because, of course, on a small scale, the tangent space is a good approximation to the manifold, to the smooth manifold. So if we take something with which we approximate the manifold, extend it in this tangent direction, we don't need to take points so closely together, sample points so closely together. And the most obvious idea how to elongate, so if our starting point are balls, the most obvious idea how to get an elongated figure in the tangent direction is to just scale these balls into tangent directions, which means these are our figures, the ellipsoids. And here's our setting. It will be a more general one than the one in Niyogi, Smale and Weinberger, because a lot of things can simply be done more generally. We don't need a smooth, so C-infinity submanifolds of R to the n. We just need C1 to have a notion of tangent spaces. Furthermore, we don't. So we still, the manifold still needs to be without boundary, but it doesn't have to be compact without boundary, actually. So it just needs to be properly embedded. This means the embedding of the manifold in the Euclidean space is a proper map. This means pre-images of compact subsets are compact subsets. The idea is that we can allow things such as, imagine hyperboloids or paraboloids, to take something in a smaller dimension, something like this. The thing can expand into the infinite, but the boundary, so to speak, has to be entirely contained in the infinity. That's the intuition behind being properly embedded. So it's just some generalization that we can get for free. And the assumption on the information that we have about this unknown manifold is that the dimension is known and the reach is known. The sample then, if it's not a compact manifold, we can't actually sample it with a finite sample, but the generalization of compactness here is being properly embedded. Here, the generalization of the finiteness is local finiteness of the sample. This means for any point in the Euclidean, every point in the Euclidean space has a neighborhood which contains only finitely many points of the sample. We want to have a bound again on how far sample points are from any point of the manifold. Again, we denote this by kappa. And then this is our notation for open ellipsoids with center P, a point which is a point on the manifold. And then if the manifold is of dimension m, therefore of codimension n minus m, we have that many minor semi-axes. And this is what we take for our measure P. Previously, P was the radius of the balls. Now it's the radius, so to speak, so the minor semi-axis in the normal direction to the manifold. But the major semi-axes are longer, and this is the maybe at first glance somewhat weird scaling, but there is a reason behind it. It doesn't actually make that much sense to have a fixed scale. So just take some fixed factor times P, because on a smaller scale, the manifold looks less curved. So we can afford ourselves more eccentric ellipsoids, and they will still will approximate the manifold. But on a larger scale, the manifold can already curve by some bit, so we can't have the ellipsoids too eccentric to still recover the homotopy type. And this is an example of a function which nicely capture this. we have written a paper already that we have recently submitted, and it's on arXiv, and there it's a longer explanation of why exactly we take this function. But here I don't have too much time to go in details, but that's the basic idea. Anyway, denote by EP the union of all of these ellipsoids, and then here's the Niyogi, Smale, Weinberger style theorem. We have again an interval for possible p's such that the union of these ellipsoids triangular deformation retracts onto n, which allows us to recover the homotopy type of n, and in particular the homology. For those interested, here are the details of what bounds we get, which again look a bit weird at first glance. But the point is that this measure of the density of the sample is actually much better now, approximately 2 times, 3-6 times improvement over the Niyogi, Smale and Weinberger. So let's examine now how we get to such a theorem, and also where we get these weird numbers and expressions from.
Davorin, could I ask a question?
Sure.
So for now, is it correct to say that you're assuming that the tangent spaces are known, so that the directions of the ellipses are known, where it could be a follow-up step to try to approximate those later? Is that correct?
It's an important question, yes, what you just mentioned. This actually has to do with Sarah's previous work. She worked on a project which was precisely about this, estimating tangent spaces from the sample.
Well, actually, so let me clarify. We didn't do the research. We just used other people's papers. That's sort of a question that has been, like, people have worked on. We implemented these ellipsoids, sort of ellipsoid-driven complexes, as we called them, and we used one of the approximations that was already sort of described in previous papers.
Wonderful, thanks.
Yeah. Just a second, someone mentioned something in the chat. What kind of density do you need to...
Davorin, what kind of density do you need to get tangent spaces? So I guess I'm not. I don't remember. I don't recall exactly the results from that paper. But while Davorin is talking, I will look it up and copy paste what we used.
Yeah. Sorry, I don't remember by heart either. But Sarah should bring the relevant information soon. But yes, this was actually about getting the theoretical framework for what Sarah previously did. So to do a theory here, although with the caveat that we're not using exactly the same kind of ellipsoids as in that previous work, where the ratio between the minor and major semi-axes was constant. But we feel that this version works better, at least based on our experience. But yes, the proof is something completely different from what Niyogi, Smale, Weinberger and other people who did similar things did, because the most straightforward idea, the normal deformation retraction, where you just deformation retract to the closest point on the manifold, simply doesn't work. And here's an example. If we take a point, even though this obviously still deformation retracts to the manifold, which is here denoted by blue, you can't do it directly. You need to curve this a little bit around to get there. And the question is then how to do this and how to avoid this problem. So here's the idea, but I'll draw pictures to so that we can actually see what's happening. So on an individual ellipsoid, what you can do is the following. First of all, this ellipsoid is of a certain size p, but consider the ellipsoids of all smaller sizes. These will foliate these ellipsoids like this. No, sorry. This is too ugly even for my standards. Okay, something like this. And then if you pick a point here which you want to determine how the deformation retracts to the manifold, it will lie on a precisely one of these ellipsoids. And then there are different possibilities where the direction towards the closest point, so the normal projection goes. So draw the tangent space onto this ellipsoid here. And if the tangent, so if the direction towards the closest point is inside this half space, leave it. If it goes outside, project this direction onto this tangent space. So what you're actually doing is projecting this direction onto this half space here. And this gives you a vector field. And the idea is basically that you go along this vector field to get to the manifold. So, for example, if we have a similar situation as in the previous picture, where you have here the next ellipsoid, so something like this, and then you would want to project outside the union of this ellipsoid. What would actually be happening is that because your directions here of the vector field will be tangent to this smaller ellipsoid, you will actually slide alongside this ellipsoid here until you reach this second one. From here, we would want to then make a turn and go to the manifold itself. Now, so long as we are only on a single ellipsoid, this is not a problem. This already works. But when we hit another ellipsoid, well, this projection won't be the same on the second ellipsoid, so we wouldn't get a well-defined vector field. So what we actually do is use partition of unity to glue together these vector fields, but it's still not good enough. On this intersection here, what we actually want somewhere in the middle is to glue this first field with the normal deformation retraction, which we then later glue this with the field on this second ellipsoid. Choose the partition of unity carefully enough, and you can do this. But to do so, you need to prove that the normal deformation retraction here on this intersection actually works. And that's actually this proves to be basically the heart of the problem. This is already fairly technical and difficult to do, but this second part, the reason why this is the most problematic is because, well, what is it that you're actually trying to prove here? You have a manifold. You're trying to capture its homotopy type with elongated figures, and what you really want to avoid is this. Here you got a new cycle. And this cycle appears because of this intersection here. And if you were trying to do the deformation retraction from here, what would happen is that on this intersection, because of this ellipsoid, you would be pulled in this direction, and because of this ellipsoid, you would be pulled in this direction, and you can't do this deformation retraction continuously. And what we're trying to prove here is that this situation is impossible. And the reason is because we didn't choose that eccentric of figures here of ellipsoids. What actually happens is that, well, first of all, you definitely want to take a sample dense enough so that you cover your manifold. Otherwise, obviously, you don't have this theorem. But this is fairly easy to calculate what you need. And then you know that this part here is necessarily covered by some ellipsoid. And what we claim here is that we have an ellipsoid which covers this part, which is thick enough here so that it also covers this entire hole. And we don't have a problem. Now, the actual, so this is just the intuition behind it. The actual situation is much more difficult because, well, things aren't happening in a nice two-dimensional plane as I'm drawing here, but I can't really draw this in n dimensions. But yes, imagine these ellipsoids. Their configurations are really random, arbitrary. So you would need to go through all of these configurations to determine that the previous situation can't happen. And furthermore, the problem is you don't know that you have a single ellipsoid which covers this entire part. You can have several of them, and then you need to determine which is the correct one so that you know that you cover this problematic point and so on. So yes, the situation is complicated, although the idea behind it is simple. Just take an arbitrary configuration, write down the conditions for all of these things, and then prove that this works. You can reduce this to a certain inequality. Yeah, in theory, sure, in practice, no. We tried to do this by hand, we didn't get anywhere. We tried to calculate these things with Wolfram Mathematica, and already starting intermediate results yielded expressions which were like dozens of pages long. We tried to continue this, and we got to hundreds of pages of intermediate expressions. We continued this a little longer, and then Mathematica just broke down. Yeah, it's too complicated. Why suddenly so complicated compared to balls? Well, it turns out that you need certain things to be, or certain vectors, or in this calculation of a specific length, and going in a specific direction. So first you need to normalize certain vectors and then multiply them by a suitable length. But this normalization in the case of balls is just dividing by the radius of the balls, which is constant. And it doesn't get complicated. But in the case of ellipsoids, it's something similar to the distance from the center of the ellipsoid, which continuously changes, and you get these square roots of sines and cosines, which very quickly proliferate in the calculation, and it just gets impossible. Okay, so this didn't work, and what we then did instead was write the C++ program. So what we're trying to prove is that the entire normal projection, the entire line segment is always covered by a single ellipsoid if we start with a point in that intersection. We wrote a program which shows that if it's not already covered by that starting ellipsoid where we took the point, we can find an ellipsoid, specifically the one. So you take your point, you find the closest point on the ellipsoid where you want to project it, you have a guaranteed to have a sample point which is at most kappa away from this point. Take that sample point and you can prove that this whole line, if it wasn't in the original ellipsoid, it has to be in that one. But you already know that the projection is in that ellipsoid, so you just need to prove that the original point is this ellipsoid because ellipsoids are convex. And that reduces to inequality, which you can reduce to a function being positive for all possible configurations. Now, if you actually do the general case, this function is dependent on 12 variables. Okay, even with the C++ program, it's too much. You won't be able to do it. It takes too much time. But with a lot of clever tricks, you can reduce the number of variables by 4, which just barely makes this feasible. Our program ran for a third of a week, almost exactly, in the latest iteration, and yeah, it calculated, it works out. But how can you prove that a function is everywhere positive with the program, since the function is defined on uncountably infinitely many values? Well, the function turns out to be Lipschitz. So if you calculate it on, and it's defined on a compact domain, so you can calculate the values of the function in a finite dense enough lattice in that domain. And if you can prove that the function, all the function values are above a certain positive lower bound, which needs to be above the steps in this lattice times the Lipschitz coefficient, well, then you know that the function, since it can't change more than the Lipschitz coefficient, can't fall too much below that lower bound, and so it still needs to be positive. That's the idea. It would actually work for any uniformly continuous function, but since the function is Lipschitz, it makes for a little bit easier of a calculation. So the very basic idea how you can reduce this to 4 variables, just one of the tricks. You don't have to actually check all the configurations. You can just check the worst cases in the sense that for every case, there is at least one case at least as bad in that set of cases. And since you're trying to prove that a certain ellipsoid always contains a particular point, the worst cases will be when A, this ellipsoid is as far away from this point as possible, and B, it is turned towards this point as close to the normal direction as possible, because along the normal direction is where we have the minor semi-axis. And then you can maximize both of these 2 conditions. And with a lot of turning around, you can also reduce much to a plane where you won't have so many free parameters. So in the end, you can do this with 4 variables. Okay, I won't go into more details because I only have 5 more minutes. But what is important to say here is that there is a price to pay to do this with the program. You can't actually reach the theoretical bound for P, which is what you want, because if you actually went to the theoretical bound, the function would come arbitrarily close to 0, so you couldn't prove the numerically calculated program that it is above a certain positive lower bound. So you sacrifice how good your end result is. And because of all of these tricks and sacrifices here in this program, you also get those weird values that you saw in the theorem. Those values are basically experimental. We just tried what was still feasible to calculate and still worked out, basically. But it led to a reasonably decent result. It was still a significant improvement over the original result. Anyway, here is something about possible future work, the improvements that one can do. First of all, obviously run the program with a tighter balance and a better hardware. What I showed you was the version of the theorem of the latest program we ran before we decided, good enough, let's submit the paper. But of course, in time one can improve this. Then the next thing is, if you try to use these results in practice, you don't have a guarantee that your sample points are exactly in the manifold. Maybe it's slightly noisy. The question is how good of a result you can get. Then, of course, if your sample point isn't directly on the manifold, then you don't have a tangent space, but you could take an approximation to this, maybe the tangent space in the closest point to the manifold, or something like this. The standard thing that people did for walls in the literature, don't do everything based on the global feature size, because then you will require the same density, even though maybe just one part of the manifold is problematic, and you would just require greater sample density just to them, and elsewhere you could do with a smaller density, so make things dependent not on the global feature size of the reach, but on local feature. So, and also something that we started to think about recently, consider other types of figures, not just ellipsoids. And so far, the optimal shape that we have come up with seems to be this one. If you imagine this in a higher dimension, this looks like a barrel. So if you imagine that your manifold goes through here, then because of the reach tau, so the radii of these balls here are tau, you know that the manifold can't go inside of these balls. Extend these balls to tau plus p, intersect them. So this is the normal direction, the vertical one, the horizontal one is the tangent direction. So extend these balls that start in the normal space like this, intersect them, and then intersect this the ball that goes through these intersection points here. These intersections of these extended balls guarantee you that you will have an optimal theoretical bound on the ratio kappa divided by tau, because this figure, you mustn't allow it to reach the medial axis, which starts here, tau away from your manifold. So you need to bound this distance here, how far this goes from here, but you also need to have a guarantee that your manifold is entirely covered by these figures, and the fastest way that the manifold can escape this figure is along this tau ball. So extend this figure to this point. That will guarantee you the best ratio, while go in this direction for as little as possible. That is why this distance here is the same as this distance here, and it lies on this wall here. But then you get these kind of figures which have this problematic tips, which are difficult to deformation retract. It is because of these tips that you need to make these curves around here. It's better to cut them away. You don't actually lose anything, because when you're trying to prove that a figure contains a particular point, you are relying on the fact that the center of that figure is at most kappa away from that point. So you can just restrict to figures which are kappa away, which is precisely this distance here. And then you get such barrels. Presumably, you can repeat the same argument for these barrels. We haven't done this yet, mostly because well, if we do the same thing, you wouldn't get that much of an improvement. It's actually, the ellipsoids are actually precisely the ones that are inside of these barrels here, inscribed, if you start from these normal points here. So you don't get a massive improvement, but we wouldn't get a massive improvement if we could do these things theoretically, not with the help of the program. The good news is the calculations are much simpler, because now the bounds, the boundaries are parts of balls. The bad news is, instead of dozens of pages, you get intermediate results which are only a third of the pages, something like this, but there it's still extremely difficult to work with all the nested roots and so on. So we haven't figured out yet how to do this by hand. But okay, let's finish here because I'm out of time, and you are invited to ask your questions.
Okay, thank you, Davorin. So before we get to questions, I would invite everyone to unmute themselves so that we can properly thank Davorin. Now questions. So as said, everybody is set to mute. So in order to ask a question, you first have to unmute yourself.
Got a comment in the chat, not a question. Thanks.
Yeah.
I wanted to ask a question, or I have a couple questions, but I'll just start with one. I don't know what approximations or non-sharp bounds were made in the Niyogi, Smale, Weinberger work, but is there any chance that, you know, a version of this computational proof, which I really like, it's really fantastic, is there any chance that or a version of that for balls could maybe find potentially even improved bounds than some of the bounds that have appeared in other papers? Or is that unlikely because many of these theoretical results are maybe close to sharp?
Yeah, I'm not entirely sure. Our methods are quite a bit different. It's possible, certainly, that some of the ideas could be used because we are still incorporating normal deformation retraction here. So at least those parts, maybe one could improve the bound. We haven't actually tried to do this though.
Mm-hmm. I'll just be impolite and ask my other question. You assumed the sample S is finite or locally finite. I was curious why that assumption is needed. Why can't you have, you know, the entire, you know, an infinite number of points sampled on the manifold?
So let me just draw here. You are still relying on compactness in the arguments, specifically compactness of those unions of ellipsoids, the local compactness really. And if you have points that converge somewhere, you potentially lose this. So you don't really need more than local compactness because, well, if you can cover your entire space with pieces where you can approximate well enough on each individual piece, well, then you have a good enough approximation on the whole thing. That is why you don't explicitly need compactness and finiteness, just local compactness and proper embeddedness. But it turns out in the arguments that you still need some form of compactness, and then you need to avoid these accumulation points of sample points.
Mm-hmm.
So it's more to avoid this, not so much the continuous sample.
Mm-hmm.
Because in the case of a continuous sample, you could still recover this local compactness.
I see. Thanks. Very nice.
More questions? Okay, so if we do not have more questions for the moment, I'm going to thank Davorin again and stop the recording, and you can continue asking questions once we're offline.